Right now, you are traveling through time at a rate that is measurably slower than most of the universe. This is not science fiction, this is physics. Every second you experience passes differently than a second experienced by someone in deep space, far from any gravitational influence. Einstein proved this in 1915, and the implications still shake the foundations of reality. Time is not universal. Time is not constant. Time bends, stretches, and breaks depending on where you are and how fast you move. We will journey through the discovery that shattered our understanding of the cosmos, explore the evidence that time is an illusion, and reveal what it means when the universe has no universal clock. If you are ready to question everything you thought you knew about time, hit that like button and subscribe. Prepare yourselves, we begin. Albert Einstein sat in the patent office in Bern, Switzerland, staring at a clock tower across the street. The year was 1905. He was 26 years old, working a day job evaluating patent applications, and in his spare time, he was dismantling the universe. The question that haunted him seemed simple. What would happen if you traveled at the speed of light? Would you see light frozen in place? The answer led to special relativity, a theory that destroyed absolute time forever. Einstein realized that the speed of light is constant for all observers, no matter how fast they move. This sounds innocent enough until you work out the implications. If light always travels at the same speed, but observers are moving at different velocities, then time itself must be flexible. Two people moving at different speeds will measure time passing at different rates. This is not an optical illusion or a measurement error. Time genuinely passes differently for them. The path to this realization was not straightforward. Einstein built on work by earlier physicists who noticed problems with the classical understanding of light and motion. In the late 1800s, James Clerk Maxwell unified electricity and magnetism into a single theory, producing equations that predicted electromagnetic waves traveling at a specific speed. This speed matched the measured speed of light, revealing that light is an electromagnetic wave. But Maxwell's equations posed a puzzle. They specified the speed of light without reference to any observer. Speed is normally relative. A car traveling at 60 miles per hour moves at that speed relative to the road, but relative to another car traveling at 50 miles per hour in the same direction. It only moves at 10 miles per hour. Yet Maxwell's equations gave a single value for the speed of light, with no mention of what it was relative to. Physicists assumed there must be a medium through which light waves travel, just as sound waves travel through air. They called this medium the luminiferous ether. The ether was supposed to fill all of space, providing the reference frame for light's speed. But if the ether existed, Earth's motion through it should create an ether wind, just as moving through air creates wind. Experiments should detect this wind by measuring whether light travels faster or slower, depending on whether it moves with or against Earth's motion through the ether. In 1887, Albert Michelson and Edward Morley conducted the most famous of these experiments. They used an interferometer, a device that splits a light beam, sends the parts along perpendicular paths, then recombines them. If light traveled at different speeds in different directions due to Earth's motion through the ether, the recombined beams would show interference patterns revealing the difference. They found nothing. No matter which direction they measured, light traveled at the same speed. This result baffled physicists. Some proposed that objects contract when moving through the ether, perfectly compensating for the expected effect. George Fitzgerald and Hendrik Lorentz developed mathematical transformations describing this contraction, but they treated it as a physical effect caused by motion through the ether. Einstein took a radically different approach. He abandoned the ether entirely. He proposed two postulates. First, the laws of physics are the same in all inertial reference frames, meaning any frame moving at constant velocity with no acceleration. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. These simple assumptions had revolutionary consequences. If light speed is constant for all observers, then measurements of space and time must vary between observers to make this work. Time dilation and length contraction are not effects of motion through some medium. They are fundamental features of spacetime itself. The famous thought experiment involves twins. One twin stays on Earth. The other twin boards a spaceship and travels at near light speed to a distant star and back. When the traveling twin returns, they have aged less than the twin who stayed home. This is the twin paradox, though it is not really a paradox. It is a prediction of relativity that has been confirmed thousands of times. Let's examine why this happens. As the traveling twin accelerates to high speed, their clock, and indeed all physical processes in their body, slow down relative to Earth. From Earth's perspective, the traveling twin moves in slow motion, but from the traveling twin's perspective, their own time passes normally. They do not feel slow. Instead, they observe that Earth's clock is running slow. This seems contradictory, but the resolution involves acceleration. The traveling twin must accelerate to high speed, decelerate at the destination star, accelerate back toward Earth, and decelerate again upon arrival. These accelerations break the symmetry. The traveling twin experiences forces during acceleration that the Earth twin does not. General relativity handles acceleration, showing that the traveling twin's path through spacetime is longer when measured in time, even though it is shorter when measured in proper time along their world line. Time dilation is real. Experiments have proven this beyond any doubt. Atomic clocks flown on airplanes run slower than identical clocks left on the ground. In 1971, Joseph Hafele and Richard Keating flew cesium atomic clocks around the world on commercial flights. When they compared these clocks to reference clocks that remained at the United States Naval Observatory, they found differences of a few hundred nanoseconds, matching the predictions of relativity to within experimental error. The eastbound clocks, flying in the direction of Earth's rotation and thus moving faster, lost time. The westbound clocks, flying against Earth's rotation and thus moving slower relative to the center of Earth, gained time. Both effects were predicted by relativity. Velocity-based time dilation from special relativity and gravitational time dilation from general relativity both contributed, and the measurements confirmed both. GPS satellites provide another compelling example. These satellites orbit at about 12,500 miles altitude, traveling at roughly 8,700 miles per hour. At this altitude, they experience weaker gravity than on Earth's surface, causing their clocks to run faster by about 45 microseconds per day. But their orbital velocity causes their clocks to run slower by about 7 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. This might sound trivial, but GPS determines position by measuring the time it takes for signals to travel from satellites to receivers. Light travels about 1 foot per nanosecond. A timing error of 38 microseconds per day would cause position errors accumulating to miles per day. GPS systems must continuously correct for relativistic effects, or they would become useless within hours. Every time you use a navigation app, you are relying on general relativity being correct. Particles called muons, created in Earth's upper atmosphere, provide yet another demonstration. Muons are unstable particles, similar to electrons but heavier. They decay into other particles with a half-life of about 2.2 microseconds when at rest. Cosmic rays, high-energy particles from space, strike atoms in the upper atmosphere, creating showers of particles including muons at altitudes around 10 miles. These muons travel toward Earth's surface at speeds close to the speed of light. Even at light speed, traveling 10 miles takes about 54 microseconds. In that time, muons at rest would have gone through about 25 half-lives, meaning only 1 in 33 million would survive to reach the ground. Yet muons are abundant at sea level. Detectors measure large numbers of them constantly. The explanation is time dilation. From Earth's perspective, the muons' internal clocks run slow due to their high velocity, extending their half-life enough that many survive the journey. From the muon's perspective, their lifetime is normal, but the distance to Earth's surface is contracted, allowing them to reach the ground before decaying. Both perspectives are correct and equivalent. Time dilation and length contraction are two sides of the same coin, but special relativity only handles constant velocities. It does not account for acceleration or gravity. Einstein spent the next decade developing general relativity, which extended the principle to all motion and incorporated gravity. The key insight came in 1907, when Einstein had what he called the happiest thought of his life. He realized that a person in free fall does not feel their own weight. If you jump off a building, during the fall, you feel weightless. This suggested that gravity and acceleration are deeply related. Einstein formulated the equivalence principle, which states that there is no experiment you can perform inside a closed laboratory to distinguish between being at rest in a lost gravitational field and being accelerated in the absence of gravity. If you stand in an elevator on Earth's surface, you feel a force pressing you against the floor. If the elevator cable breaks and you go into free fall, that force vanishes. But you would feel exactly the same sensations if the elevator were in deep space, far from any gravity, and being accelerated upward at 9.8 meters per second squared. The two situations are equivalent locally. This equivalence led Einstein to a radical conclusion. Gravity is not a force in the Newtonian sense. Gravity is the curvature of space-time itself. Massive objects like planets and stars warp the fabric of space and time around them. Objects moving through this warped space-time follow curved paths, which we perceive as gravitational attraction. The Earth orbits the Sun not because some force pulls it inward, but because the Sun bends space-time, and the Earth follows the straightest possible path through that curved geometry. In flat space-time, the straightest path is a straight line. In curved space-time, the straightest path is a curve called a geodesic. Planets orbit stars, moons orbit planets, and light bends around massive objects because they are all following geodesics through curved space-time. This has a profound consequence for time. In regions of strong gravity, time passes more slowly. If you stand at sea level, time runs slower for you than for someone on a mountaintop. The difference is tiny, just a few nanoseconds per day, but it is measurable and real. Modern atomic clocks are sensitive enough to detect time dilation from height differences of mere centimeters. If you raise an atomic clock 1 foot, it ticks faster. Gravity weakens with distance from Earth's center, so the higher clock experiences slightly less gravity and slightly faster time. This has been confirmed experimentally by comparing clocks at different elevations. The predictions of general relativity match observations with incredible precision. Near a black hole, where gravity is extreme, time dilation becomes dramatic. An observer falling toward a black hole would experience time normally from their perspective. They would cross the event horizon, the point of no return, in finite, proper time, perhaps seconds or minutes depending on the black hole's mass. But to a distant observer watching them fall, they would appear to slow down, moving ever more sluggishly as they approach the horizon. Light emitted by the falling observer becomes increasingly redshifted, stretched to longer wavelengths, and dimmed. Eventually, the falling observer appears to freeze just above the event horizon, their image fading to invisibility as the light becomes too redshifted and faint to detect. From the distant observer's frame of reference, the falling person genuinely takes infinite time to reach the event horizon, asymptotically approaching it, but never quite crossing. This is not just appearance. From the distant observer's frame of reference, the event of crossing the horizon lies infinitely far in the future. Both perspectives are correct within their own reference frames, illustrating the relativity of simultaneity in curved space-time. The falling observer crosses the horizon at a specific proper time on their clock. The distant observer never sees them cross. There is no contradiction because simultaneity is relative. The event of crossing the horizon is simultaneous with different events for different observers. This becomes even stranger when you consider Hawking radiation. Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate. From the distant observer's perspective, infalling matter never quite crosses the horizon before the black hole evaporates. Yet from the infalling perspective, they cross long before evaporation matters. Reconciling these perspectives is a deep problem in theoretical physics related to the black hole information. Paradox. The universe has no universal clock. There is no single timeline that all observers agree on. Every object in the universe experiences its own personal time, determined by its velocity and the gravitational field it occupies. This shatters our intuitive understanding of reality. We think of time as a river carrying all of us forward together at the same rate. But time is more like a landscape of rivers, each flowing at different speeds, intersecting and diverging, with no master current. You cannot say what time it is in the universe. You can only say what time it is for a specific observer in a specific location, moving at a specific speed. This leads to profound questions about the nature of existence and reality itself. If time is relative, what does it mean to exist? Do past events still exist somewhere, or are they gone? Do future events already exist, waiting to be experienced, or are they yet to come into being? When you factor in that the universe is expanding, the problem becomes even more complex. Cosmologists use something called cosmic time, which is the time measured by observers at rest with respect to the cosmic microwave background radiation, the afterglow of the Big Bang. This provides a useful reference frame, but it is still just a choice of perspective, not an absolute timeline. Observers moving at high velocity relative to the CMB would measure different times since the Big Bang. In principle, you could travel fast enough that from your perspective, the universe is only a few years old, even though 13.8 billion years have passed in cosmic time. The cosmic time convention works because the universe is highly homogeneous and isotropic on large scales. On average, matter is distributed uniformly and looks the same in all directions. This symmetry allows cosmologists to define a preferred reference frame and a global time coordinate. But this is a convenience, not a fundamental property. The universe does not objectively have an age, independent of the observer. The flexibility of time leads to scenarios that sound like science fiction but are established physics. Imagine two astronauts who synchronize their watches before one travels to orbit a neutron star, a superdense collapsed core of a dead star with gravity so strong that time dilation is significant. The neutron star might have a mass similar to the Sun, compressed into a sphere only 12 miles in diameter. At the surface, gravitational acceleration is about 100 billion times stronger than on Earth. Orbiting close to such an object, the astronaut experiences intense time dilation. After what feels like 1 year to the orbiting astronaut, they return to their companion waiting in a distant spacecraft. The companion's watch shows that 10 years have passed. Both are correct. Both experience time passing normally for themselves, but they aged at different rates. They lived through different durations of time. The orbiting astronaut genuinely experienced less time. Their biological processes, heartbeat, thoughts, and the radioactive decay of atoms in their body all proceeded more slowly from the perspective of the distant astronaut. But from their own perspective, nothing seemed abnormal. This is the essence of time dilation. You cannot say which one experienced the real time. Both did. This raises the question of whether time even exists as a fundamental feature of reality, or if it is an emergent property arising from something deeper. Some physicists argue that time is not fundamental. They propose that the true laws of the universe are timeless, and that the appearance of time emerges from the way we interact with quantum systems. In this view, time is like temperature. Temperature is not a fundamental property of individual atoms. It is a statistical description of how atoms move collectively. An individual atom does not have a temperature. Only a large collection of atoms has a well-defined temperature. Similarly, time might be a way of describing change in a fundamentally timeless universe. The fundamental laws would be symmetric with respect to time, having no preferred direction, and the appearance of time would emerge from statistical properties of large systems. Others believe time is real, but that the direction of time, the difference between past and future, is not fundamental. The laws of physics, with few exceptions, work the same whether time runs forward or backward. Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's equations of general relativity, and Schrödinger's equation in quantum mechanics are all time-symmetric. A movie of two billiard balls colliding looks equally valid played forward or in reverse. The trajectories obey the laws of physics in both directions, yet we only experience time flowing one way. We remember the past, but not the future. We see eggs break but not unbreak. Entropy increases, but never spontaneously decreases. Why? The answer seems to lie in entropy, a measure of disorder in a system. The second law of thermodynamics states that entropy always increases in a closed system. This gives time a direction. The past is the direction of lower entropy. The future is the direction of higher entropy. But this raises another mystery. Why was the entropy of the early universe so low? The Big Bang started with incredibly ordered conditions, all the energy and matter concentrated in a tiny volume with low entropy. Over time, the universe expanded and entropy increased, creating the arrow of time we observe. But why did it begin with low entropy? That question remains unanswered and is one of the deepest mysteries in physics. If the initial state of the universe were chosen at random from all possible states, it would almost certainly have high entropy. Low entropy states are rare, fantastically improbable, yet the universe began in one. This suggests the initial conditions were not random, but were somehow special or constrained. Understanding why is a major unsolved problem. One proposal is that the low initial entropy is explained by cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, a tiny patch of space expanded by an enormous factor, perhaps doubling in size every 10 to the negative 35 seconds for a duration of around 10 to the negative 32 seconds. This smoothed out any irregularities, creating a nearly uniform low entropy state. After inflation ended, the energy driving inflation decayed into particles and radiation, reheating the universe and initiating the hot Big Bang phase we normally think about. Inflation explains several puzzles in cosmology, including why the universe is so uniform and why its geometry is nearly flat. It also provides a mechanism for the low initial entropy. However, inflation itself requires specific initial conditions. Why did inflation occur? What set up the initial state that allowed inflation to start? This pushes the problem back, but does not fully solve it. Some theorists propose eternal inflation, where inflation never truly ends, but spawns an infinite number of separate bubble universes, each beginning with its own Big Bang. In this multiverse scenario, initial conditions vary across bubbles, and we find ourselves in one with low entropy because only such universes allow complex structures and observers to exist. Understanding time dilation requires understanding spacetime geometry, which is not intuitive. We experience 3 dimensions of space: up and down, left and right, forward and backward. We can move freely in any spatial direction. Time feels different. We only move forward in time, never backward, and we cannot stop. But relativity treats time as a 4th dimension, similar to the spatial dimensions but with different mathematical properties. Together, the 3 spatial dimensions and 1 time dimension form a 4-dimensional continuum called spacetime. Events in the universe are not located in space at a particular time. They are located in spacetime as 4-dimensional coordinates. Your entire life, from birth to death, exists as a path through spacetime called a world line. From this perspective, the past, present, and future all exist simultaneously. Your world line intersects other world lines. Those intersections are the events where you interact with other objects or people. This view, called the block universe, suggests that time does not flow. Instead, All moments exist eternally in spacetime, and our perception of time flowing is an illusion created by our consciousness moving along our world line. Imagine a movie. The entire film exists as a sequence of frames on a reel. When you watch the movie, you experience one frame at a time, creating the illusion of motion and time passing. But all the frames exist simultaneously on the reel. The block universe proposes that space-time is like that movie. All moments exist, and consciousness experiences them sequentially, creating the sensation of time flowing. This is philosophically unsettling. It implies that the future already exists in some sense, even though we have not experienced it yet. It suggests that free will might be illusory because all our choices are already laid out in space-time. If the future exists, is it fixed? Can we change it? Or is everything predetermined? Physicists debate whether the block universe is the correct interpretation, but it is consistent with relativity. Some philosophers and scientists resist this conclusion, arguing that it conflicts with our direct experience of time passing and with quantum mechanics, which seems to require an open future where probabilities collapse into definite outcomes. In quantum mechanics, before you measure a particle's position, it does not have a definite position. It exists in a superposition of all possible positions simultaneously. When you measure it, the superposition collapses, and the particle that appears in one location, this collapse seems to require the passage of time. Before the measurement, the system is in one state. After the measurement, it is in another state. This suggests time is fundamentally real, not just an illusion. However, some interpretations of quantum mechanics, like the many worlds interpretation, avoid collapse by proposing that all possible outcomes occur, each in a separate branching universe. In this view, there is no collapse, no fundamental passage of time, just an ever-branching structure of possibilities. The relationship between quantum mechanics and general relativity is one of the great unsolved problems in physics. General relativity describes gravity and space-time curvature. Quantum mechanics describes the behavior of particles at tiny scales. Both theories are extraordinarily successful in their domains, but they are fundamentally incompatible. General relativity treats space-time as a smooth, continuous fabric. Quantum mechanics requires that everything, including space-time itself, should be quantized, existing in discrete chunks. Physicists have tried for decades to develop a theory of quantum gravity that unifies these frameworks. Candidates include string theory, loop quantum gravity, causal set theory, and others, but none have been experimentally confirmed. Understanding quantum gravity might resolve the mysteries of time, revealing whether time is fundamental or emergent, continuous or discrete, real or illusory. One prediction of quantum gravity is that space-time itself might have a granular structure at the smallest scales. The Planck scale, which is about 10 to the negative 35 meters in length and 10 to the negative 43 seconds in time. These are unimaginably small. To get a sense of scale, the Planck length is to an atom what an atom is to a large planet. At this scale, space-time might consist of discrete units, quanta of space and time, rather than being smooth. Time might not flow continuously, but instead advance in tiny discrete steps, like frames in a movie. Each frame represents one Planck time, and the universe progresses from frame to frame. If true, this would revolutionize our understanding of reality. It would mean that time has a fundamental smallest unit, a chronon, and that nothing can happen faster than one chronon. This would resolve some paradoxes in physics and provide a natural cutoff for infinities that plague quantum field theories. But detecting effects at the Planck scale is currently impossible. The energies required are beyond anything we can create with particle accelerators, and the distances are far smaller than anything we can measure with any conceivable technology. Even without quantum gravity, general relativity predicts phenomena so bizarre that they challenge our sanity. Black holes are the most famous example. When a massive star exhausts its fuel, it can collapse under its own gravity, compressing its mass into an infinitely small point called a singularity. Around the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. The event horizon is not a physical surface. It is a mathematical boundary in spacetime defined by the property that light emitted exactly at the horizon can neither escape nor fall inward. It stays at the horizon forever. Light emitted just inside the horizon falls toward the singularity. Light emitted just outside can escape to distant space. The radius of the event horizon is called the Schwarzschild radius, after Karl Schwarzschild, who found the first exact solution to Einstein's equations describing a black hole. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it would be about 9 millimeters. Compress any object smaller than its Schwarzschild radius, and it becomes a black hole. Time behaves so strangely near black holes that the normal rules of cause and effect break down. As mentioned earlier, to an outside observer, objects falling into a black hole appear to freeze at the event horizon, never quite crossing it. Light emitted by the falling object becomes redshifted, its wavelength stretched. As the object approaches the horizon, the redshift increases without bound. The light becomes infrared, then radio waves, then wavelengths meters, kilometers, light years long. The photons arrive less and less frequently. Eventually, the rate drops below 1 photon per age of the universe. The object effectively disappears, frozen at the horizon from the external perspective. From the perspective of the falling object, however, things are completely different. They cross the horizon in finite proper time and plunge toward the singularity. From their point of view, nothing special happens at the horizon. There is no wall, no barrier. They might not even notice when they cross because locally, spacetime looks nearly flat. Only when they look outward do they see something strange. Light from the external universe becomes blue-shifted and compressed. The entire future history of the universe appears to play out in fast forward before they reach the singularity. Both perspectives are correct within their own reference frames, but they describe completely different experiences. Inside the event horizon, the roles of space and time swap. Outside a black hole, you can move freely in space. You can go left or right, up or down, forward or backward, at will. But you cannot control your motion in time. You are dragged forward inexorably. Inside a black hole, this reverses. You can, in principle, move freely in time, forward or backward, though this is only a formal mathematical property and has strange interpretations. But you cannot control your motion in space. Specifically, you cannot control your motion in the radial direction toward the singularity. The singularity is not a place in space. It is a moment in your future, an unavoidable point in time that you will reach no matter what you do. Just as you cannot avoid tomorrow outside a black hole, you cannot avoid the singularity inside one. This is mind-bending. The singularity is when you will reach it, not where. At the singularity, space-time curvature becomes infinite, and the known laws of physics break down. We do not know what happens there. General relativity predicts its own failure. This suggests that a deeper theory, presumably quantum gravity, is needed to describe the singularity. The mathematics of black holes reveal other strange features. Rotating black holes, described by the Kerr solution, have additional structure. They have an outer event horizon and an inner Cauchy horizon. Between these horizons is a region called the ergosphere, where spacetime is dragged around by the black hole's rotation. Inside the ergosphere, you cannot remain stationary. You must rotate with the black hole. Even light is dragged along. This frame-dragging effect exists around any rotating mass, including Earth, but for normal objects, it is incredibly weak. Around a rotating black hole, it becomes extreme. The ergosphere offers, in principle, a way to extract energy from the black hole through a process called the Penrose process. By dropping an object into the ergosphere at the right trajectory, splitting it into 2 pieces, and allowing one piece to fall into the horizon while the other escapes, you can extract energy from the black hole's rotation. the escaping piece has more energy than the original object. The black hole slows down slightly, losing rotational energy. This is not science fiction. It is allowed by general relativity, though actually performing it would require extraordinary engineering. Rotating black holes also have a feature called the ring singularity. Instead of a point singularity like in a non-rotating black hole, the singularity in a rotating black hole forms a ring shape. The mathematics suggests that you might pass through the ring without hitting it, entering a region of negative space or a different universe altogether. This is highly speculative and probably not physically realistic. Quantum effects near the singularity are expected to prevent such exotic behavior. Some solutions even allow closed time-like curves, paths that loop back in time near the ring singularity. If these exist, they would permit time travel to the past, creating paradoxes. Most physicists believe that something prevents this, perhaps quantum effects that create infinities destroying the spacetime structure before closed time-like curves form. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics prevent time travel to the past, but this remains unproven. Black holes also create paradoxes that challenge our understanding of information and time. The black hole information paradox arises from combining quantum mechanics with general relativity. According to quantum mechanics, information cannot be destroyed. If you know the exact quantum state of a system at one time, you can in principle calculate its state at any future time. The evolution is deterministic and reversible, but black holes seem to destroy information. If you throw a book into a black hole, the information in that book, the arrangement of ink on pages, the words, the ideas, seems to vanish forever, erased when the book is consumed by the singularity. However, Stephen Hawking discovered that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon, a process called Hawking radiation. Over extremely long timescales, a black hole will evaporate completely, leaving only radiation. The problem is that Hawking radiation, as originally calculated, is random and thermal. It carries no information about what fell into the black hole. This means the information appears to be destroyed, violating quantum mechanics. This paradox has occupied some of the brightest minds in physics for decades. Various solutions have been proposed. Some argue that information is encoded in the Hawking radiation in subtle ways we have not yet understood. Perhaps the radiation is not perfectly thermal, but contains tiny correlations that preserve information. Others propose that information is preserved in remnants left after the black hole evaporates, tiny Planck-scale objects containing all the information. Still others suggest that the paradox reveals a fundamental conflict between quantum mechanics and general relativity, pointing toward the need for a new theory. Recent work involving holography and the AD-SCFT correspondence suggests that information might be preserved on the event horizon itself, encoded in a two-dimensional surface, even though the black hole is three-dimensional. This holographic principle has deep implications, suggesting that the universe itself might be fundamentally two-dimensional, with the three-dimensional reality we experience being a projection or hologram from that surface. The holographic principle emerged from studying the entropy of black holes. Jacob Bekenstein proposed that a black hole has entropy proportional to the area of its event horizon, not its volume. This was puzzling because entropy usually relates to the number of microstates, the different ways to arrange a system, which should depend on volume. Stephen Hawking confirmed Bekenstein's formula using quantum field theory in curved spacetime. The entropy of a black hole is proportional to its horizon area measured in Planck units. This suggests that the information content of a region of space is limited by the area of its boundary, not its volume. Gerard Hooft and Leonard Susskind generalized this into the holographic principle, proposing that the description of a volume of space can be encoded on a lower dimensional boundary to that region. In one realization, the AD-SCFT correspondence discovered by Juan Maldacena, a gravitational theory in a higher dimensional space, is exactly equivalent to a quantum field theory without gravity on the boundary of that space. This duality suggests that gravity and spacetime themselves might be emergent, arising from more fundamental quantum information on the boundary. Time travel is another consequence of general relativity that sounds impossible but cannot be ruled out by physics. General relativity allows solutions where closed time-like curves exist, paths through spacetime that loop back on themselves. An object following such a path would travel into its own past. Several scenarios could create closed time-like curves. Rotating black holes, called Kerr black holes, have geometries so warped that paths exist connecting a point in spacetime to an earlier point. If you orbit a Kerr black hole in the right way, circling near the event horizon in the direction of rotation, you could emerge before you started. Wormholes, hypothetical tunnels connecting distant regions of spacetime, could potentially allow backward time travel if one mouth of the wormhole were accelerated to near light speed relative to the other, creating a time difference between the two ends. Traveling through the wormhole would then transport you to an earlier time. Cosmic strings, theoretical one-dimensional defects in spacetime left over from phase transitions in the early universe, might allow time travel if two of them passed each other at high speed. The warped spacetime around them could create closed time-like curves. However, time travel creates paradoxes that suggest it might be impossible despite the mathematical allowances in general relativity. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, you could not travel back in time to prevent their meeting. This is a logical contradiction. Several resolutions have been proposed. The consistency principle, sometimes called the Novikov self-consistency principle, suggests that the universe forbids paradoxes. If you try to kill your grandfather, you will always fail. Perhaps your gun jams, or you miss, or you realize the person you thought was your grandfather was actually someone else, or you cause events that lead to your grandparents meeting in a different way. The universe conspires to maintain consistency. The timeline is fixed, and any attempt to change the past becomes part of the past that always happened. Another resolution is the many worlds interpretation applied to time travel. When you travel back in time, you create a branching timeline. In the new timeline, your grandfather never meets your grandmother, and a version of you is never born in that branch. But you still exist because you came from the original timeline. This avoids paradox by allowing multiple histories. However, this requires a specific interpretation of quantum mechanics and a mechanism for branching, which is not fully understood. It also raises questions about which branch you experience, and whether your actions in the past branch have any effect on your original timeline. If not, time travel becomes less interesting because you cannot change your own past. You can only create alternate timelines. Some physicists argue that time travel to the past is impossible for other reasons. Creating closed time-like curves or traversable wormholes requires exotic matter with negative energy density. Such matter has never been observed and may not exist. In quantum field theory, the vacuum energy can be negative in certain configurations due to the Casimir effect, but only in very limited ways. Producing enough negative energy to hold open a wormhole or create a time machine would require enormous amounts, possibly violating energy conditions that most physicists believe must hold. Even if it does exist, the amounts required might be prohibitively large, requiring the energy of an entire star or galaxy. Quantum effects might also prevent time machines from functioning. When a closed, time-like curve forms, quantum fluctuations could become amplified, traveling around the loop and building up to infinite energy densities that destroy the time machine before it can be used. This is called the chronology protection conjecture, proposed by Stephen Hawking, though it remains unproven. Time travel to the future, on the other hand, is straightforward and does not create paradoxes. By traveling at high speeds, or spending time near massive objects, you experience less time than distant observers. When you return, you arrive in their future. This is one-way time travel and is fully consistent with relativity. If you travel at 99.9% of the speed of light for what feels like 1 year, about 22 years pass on Earth. You emerge 22 years in Earth's future, having aged only 1 year. This is not speculative, it is a direct prediction of special relativity. The only obstacle is practical. Accelerating a spaceship to such speeds requires enormous energy, but in principle, there is no physics preventing it. Astronauts on the International Space Station experience this effect at a tiny level. They orbit at high speed and in weaker gravity, so they age microseconds less than people on Earth. They travel microseconds into Earth's future with each orbit. Over a career, an astronaut might gain a fraction of a second. The nature of time becomes even stranger when we consider the universe's beginning. The Big Bang was not an explosion in space. It was the beginning of space itself, and also the beginning of time. Before the Big Bang, there was no before. Time did not exist. This statement sounds absurd. How can time begin? What does it even mean to say there was no before? These questions push language and intuition to their limits. In general relativity, time is part of spacetime, and spacetime began at the Big Bang. The Big Bang is a singularity, a point where spacetime curvature becomes infinite and the Phi equations break down. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question does not make sense because it assumes a direction that does not exist. At the North Pole, all directions are south. There is no north. Similarly, at the Big Bang, all directions in time are forward. There is no before. However, some cosmological models propose scenarios where time existed before the Big Bang. Cyclic models suggest the universe undergoes infinite cycles of expansion and contraction, with each Big Bang followed by a big crunch, which then triggers another Big Bang. In these models, time is eternal, with no beginning. The current Big Bang is just one event in an infinite sequence. Evidence for cyclic models is lacking, but they are not ruled out. Another possibility is the ekpyrotic scenario, where our universe is a three-dimensional membrane floating in a higher dimensional space. The Big Bang occurred when our membrane collided with another membrane. Before the collision, time existed on the membrane, so there was a before. These models avoid the singularity problem by invoking extra dimensions and alternative physics. Other models invoke quantum mechanics to avoid the singularity at the Big Bang. In quantum cosmology, the universe might have originated from a quantum fluctuation in a timeless state. The wave function of the universe describes all possible configurations, and the Big Bang corresponds to the universe transitioning from a quantum superposition to a classical state. In these models, time emerges gradually as the universe evolves, starting from a regime where the concept of time does not apply. This is speculative and currently beyond experimental verification, but it shows that physicists are willing to question even the most basic assumptions about time. Stephen Hawking and James Hartle proposed the no-boundary proposal, where the universe has no boundary in imaginary time, a mathematical trick that treats time as a spatial dimension at very early moments. This avoids the singularity and suggests that asking what came before the Big Bang is meaningless because time itself smoothly transitions into space in the extreme past. If time can begin, can it also end? Some scenarios predict a far future where time effectively stops. If the universe continues expanding forever and dark energy remains constant, eventually all galaxies outside our local group will recede beyond the cosmic horizon. The observable universe will shrink to just the Milky Way and a few nearby galaxies bound by gravity. Star formation will cease as gas is exhausted. Stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, even black holes will evaporate via Hawking radiation. A solar mass black hole takes about 10 to the 67 years to evaporate. A supermassive black hole with 1 billion solar masses takes about 10 to the 100 years. These timescales are so long that they make the current age of the universe, a mere 13.8 billion years, seem like an instant. But eventually, all black holes evaporate, leaving only a dilute sea of particles and radiation. In this far future, entropy approaches its maximum. The universe reaches a state of maximum disorder called heat death. When entropy is maximized, no further change is possible because all processes that increase entropy have already occurred. Without change, time loses meaning. Clocks could still tick, in principle, counting oscillations, but nothing would happen. No events would mark the passage of time. All matter would be in thermal equilibrium, with no temperature gradients, no flows of energy, no chemical reactions. In this sense, time ends not with a dramatic event, but with a gradual fading into changelessness. This is sometimes called the heat death of the universe or the Big Freeze. It represents a future where the arrow of time vanishes because there are no longer gradients in entropy to distinguish past from future. The universe becomes static, unchanging, timeless. Of course, this assumes dark energy remains constant and the universe expands forever. If dark energy changes, the fate of the universe could be different. If dark energy strengthens over time, it could lead to a big rip. As expansion accelerates, dark energy would eventually overcome all other forces. First, galaxy clusters would be torn apart, then galaxies themselves, then solar systems, then planets and stars. Eventually, even atoms would be ripped apart as space expands faster than the forces holding them together can counteract. The big rip would occur at a finite time in the future, a moment when the expansion rate becomes infinite. This would be a dramatic end to time, a singularity in the future rather than the past. If dark energy weakens or reverses, expansion could halt and reverse, leading to a big crunch where the universe collapses back into a singularity. All the galaxies would begin moving toward each other. The cosmic microwave background would blue shift and heat up. Stars would merge, black holes would coalesce, and eventually all matter and energy would compress into an infinitely dense point. Time would end at the Big Crunch singularity, mirroring the Big Bang. If the universe is cyclic, the Big Crunch might trigger a new Big Bang, and time would continue in a new cycle. But in a simple Big Crunch, time ends. These scenarios depend on the properties of dark energy, which we do not fully understand. Current observations suggest dark energy is consistent with a cosmological constant, unchanging, and leading to eternal expansion and eventual heat death. But we cannot be certain. The measurement of time itself is far more complex than most people realize. Ancient civilizations measured time by the sun's position, defining a day as the time between successive sunrises. This seems straightforward, but it is already complicated. Earth's orbit around the sun is elliptical, not circular, causing the sun's apparent speed across the sky to vary throughout the year. When Earth is closer to the sun, it moves faster in its orbit, making the sun appear to move faster across the sky. When Earth is farther away, it moves slower. Additionally, Earth's rotational axis is tilted relative to its orbital plane, causing the sun's path across the sky to change with seasons. These effects combine to make a solar day. The time from one solar noon to the next vary by about 30 seconds over the year. Astronomers define a mean solar day, averaged over the year, to create a more uniform measure. Even then, Earth's rotation is not constant. It is gradually slowing due to tidal friction from the Moon. The Moon's gravity pulls on Earth's oceans, creating tides. The tidal bulges are not perfectly aligned with the Moon due to friction and the time it takes water to flow. This creates a torque that slows Earth's rotation and simultaneously transfers angular momentum to the Moon, causing it to gradually recede from Earth. Days are getting longer by about 1.7 milliseconds per century. Hundreds of millions of years ago, a day was significantly shorter, perhaps 22 hours. Fossil records of growth rings in ancient corals support this. Hundreds of millions of years in the future, days will be longer. This means the day is not a reliable long-term unit of time. Moreover, Earth's rotation varies on shorter timescales due to factors like atmospheric winds, ocean currents, melting ice. and even large earthquakes that redistribute mass and change Earth's moment of inertia. Modern time measurement uses atomic clocks, which are based on the oscillations of atoms, specifically the transitions between energy levels in cesium atoms. A cesium atomic clock defines the second as exactly 9,192,631,770 cycles of radiation, corresponding to the transition between two hyperfine levels of the ground state of cesium-133. This is extraordinarily precise, with the best atomic clocks accurate to within 1 second over hundreds of millions of years, or better. Recent optical atomic clocks using strontium or ytterbium are even more precise, losing less than 1 second over the age of the universe. Yet even atomic clocks are subject to time dilation. An atomic clock at sea level runs slower than one on a mountaintop because of the difference in gravitational potential. An atomic clock moving at high speed runs slower than a stationary one due to velocity-based time dilation. GPS satellites carry atomic clocks and must account for both effects. The satellites are moving at high speed relative to Earth's surface, which slows their clocks due to special relativity, but they are also at higher altitude, experiencing weaker gravity, which speeds their clocks due to general relativity. The two effects do not cancel perfectly. For GPS satellites, the gravitational effect dominates, and the clocks run faster by a net of about 38 microseconds per day compared to ground clocks. GPS receivers must correct for this difference. Without corrections, position errors would accumulate at a rate of about 10 kilometers per day. The system would be useless for navigation. This is a practical demonstration that general relativity is not just abstract theory. It affects everyday technology. Every time you check your phone's map app, you are relying on corrections for both special and general relativity. International Atomic Time, abbreviated TAI, is the weighted average of over 400 atomic clocks in laboratories around the world. This provides a highly stable and precise timescale. However, TAI is not synchronized with Earth's rotation. As Earth's rotation slows, the solar day drifts out of sync with atomic time. To keep them aligned, leap seconds are occasionally added to Coordinated Universal Time, abbreviated UTC, the civil time standard used worldwide. When a leap second is added, the last minute of a day contains 61 seconds instead of 60, with the extra second labeled 23 hours 59 minutes and 60 seconds. This keeps UTC within 0.9 seconds of UT1, a timescale based on Earth's rotation. Leap seconds are controversial because they cause problems for computer systems and networks that assume time always advances smoothly. Software must be written to handle the discontinuity. Some systems have failed when leap seconds occurred because programmers did not anticipate them. Some propose abolishing leap seconds and allowing solar time and atomic time to drift apart. Over centuries, this drift would become noticeable. Solar noon, when the sun is highest in the sky, would gradually shift. In a few thousand years, it could differ by an hour from clock noon. Proponents of abolishing leap seconds argue that modern life is governed by atomic time, not solar time, and that the cost of maintaining synchronization is not worth the benefit. Others argue that maintaining the connection to Earth's rotation is culturally and practically important. Navigation, astronomy, and satellite tracking all depend on knowing the relationship between time and Earth's orientation. This debate highlights the tension between different definitions of time. Is time something we measure from nature, like Earth's rotation, or is it something we define with atomic precision? Philosophers have debated the nature of time for millennia. Ancient Greek philosophers like Heraclitus emphasized change and flux, arguing that everything is constantly changing and that permanence is an illusion. His famous saying, "You cannot step into the same river twice," captures this view. The river is constantly flowing. By the time you step in a second time, it is different water. You too have changed. Nothing remains the same. Parmenides, in contrast, argued that change is an illusion and that reality is a static, unchanging whole. According to Parmenides, the senses deceive us into thinking things change. But true reality, accessible only through reason, is eternal and immutable. These opposing views echo in modern physics. Does time genuinely flow, with the present moment being somehow privileged and the future truly open? Or is time just another dimension like space, with all moments existing equally in the block universe? Immanuel Kant argued in the 18th century that time is not a feature of the external world, but a form of human intuition, a way our minds organize sensory experience. In this view, time does not exist independently. It is a framework we impose on reality to make sense of it. We cannot perceive things except as occurring in time, but time itself is not something we perceive. It is the condition for perception. This is similar to how space is a form of intuition. We perceive objects as existing in space, at locations, but space itself is not an object we see. It is how we structure our visual field. Kant's view is that time and space are features of how our minds work, not features of the universe independent of minds. Modern physics does not support this fully, since relativity shows that space-time has properties independent of observers, like curvature. But Kant's insight that time might be partly subjective remains relevant when considering the phenomenology of temporal experience. Modern physics leans toward the block universe interpretation, where time is real but does not flow. However, this conflicts with our subjective experience. We feel time passing. We remember the past, but not the future. We perceive the present as uniquely real in a way that the past and future are not. This is sometimes called the passage of time or the flow of time, and it is deeply puzzling from a physics standpoint. The equations of relativity do not include any term representing flow. They describe space-time as a static four-dimensional geometry where events just exist at their coordinates. Time is treated identically to space, just with a different metric signature. An event's time coordinate is no more special than its space coordinates. Yet we experience time fundamentally differently from space. Some physicists and philosophers argue that the flow of time is a psychological phenomenon, emerging from the way our brains process information and build memories. Our brains operate in a particular direction in time, accumulating memories of the past but not the future. This asymmetry in memory creates the sensation of time flowing from past to future. If you could remember the future as vividly as you remember the past, the distinction might vanish. Your sense of now would be different. The flow of time might be an artifact of how brains function as thermodynamic systems that record entropy-increasing processes. Others believe the flow points to something missing in our physical theories, a fundamental aspect of reality that we have not yet understood. Perhaps the equations are missing something essential about time. Perhaps the block universe is not the whole story. The philosopher J.M.E. McTaggart famously argued that time is unreal based on a logical analysis of temporal properties. He distinguished between the A series and the B series. The A series orders events as past, present, or future. An event is first future, then becomes present, then becomes past. This seems to describe how we experience time. The B series orders events as earlier than or later than each other. Event X is earlier than event Y. This is a permanent, unchanging relation. If X is earlier than Y, this is always true. McTaggart argued that the A series is essential for time because it captures change and becoming. Events in the B series just sit there in a fixed order. They do not change. But the A series leads to contradiction. An event cannot be simultaneously past, present, and future, yet it must have all three properties at different times. To say that an event is past means it was present, but was present refers to a time in the past, so we need a second level of time to describe the first level. This leads to an infinite regress. McTaggart concluded that time is unreal. His argument is controversial and has been extensively debated. Most physicists ignore it, focusing on the B series, which is sufficient for relativity. Events are simply earlier or later relative to each other. No flowing now is needed. The block universe uses the B series. all events exist in spacetime with unchanging temporal relations. Your birth is earlier than you're reading this text. This relation never changes. But many philosophers argue that the A series captures something essential about time that the B series misses. The experience of the present moment feels real and privileged. The open future feels different from the fixed past. Some propose a tensed theory of time, where the present is ontologically special and only the present exists. Past events no longer exist. Future events do not yet exist. This contradicts relativity, which shows that simultaneity is relative. Different observers disagree on which events are present. But advocates of tense time argue that relativity describes the structure of space-time, not the flow of time, and that a preferred foliation might exist even if undetectable. Yet the phenomenology of time, our direct experience, seems to require something like the A series. We experience the now as real and moving forward. This is called the specious present, the interval of time that feels like now. Psychologists have measured this interval at roughly 2 to 3 seconds. Anything within the specious present feels simultaneous or continuous. Events separated by more than a few seconds feel distinctly separated in time. This duration is related to the integration time of our sensory and cognitive systems. Our brains do not process information instantaneously. They integrate data over a short time window to create a coherent perceptual experience. For example, when you hear a sentence, your brain integrates the sounds over a few seconds to parse the words and meaning. The specious present is the window of integration. The flow of time might be a byproduct of this integration process, combined with memory formation. We remember past integration windows, creating the impression that time is passing, even though from a physics standpoint, all moments simply exist in space-time. Each moment of consciousness integrates information from a short time window and compares it to memories of past windows. This creates a narrative of change and progression. The sense of now is the current integration window. The sense of past is the memory of previous windows. The sense of future is the anticipation of upcoming windows based on patterns in memory. This psychological explanation does not require any flow in the physical world. It only requires that our brains operate as causal systems that record information asymmetrically in time. The psychology of time perception is fascinating and complex. Time seems to pass faster when we are busy or enjoying ourselves, and slower when we are bored or in pain. This is not just a subjective feeling. The brain genuinely processes temporal information differently in different contexts. Attention, emotion, and memory all influence how we perceive duration. When you are engaged and focused, your brain does not allocate as many resources to monitoring time itself. You lose track of time. When you are bored, you are hyper-aware of time, constantly checking how much has passed. Each check reinforces the feeling that time is dragging. Emotion also affects time perception. Threatening or emotionally intense situations seem to unfold in slow motion. People who survive car accidents or falls often report that time seemed to slow down, allowing them to perceive details they would normally miss. Experiments suggest this is a memory effect, not a perceptual one. During intense events, the brain records memories with more detail. The amygdala, involved in emotional processing, enhances memory encoding. When you recall the event, the richness of the memory makes it seem like it lasted longer than it did. Researchers tested this by having subjects free fall from a tower while trying to read rapidly flashing numbers on a device. If time truly slowed perceptually, they should be able to read faster flashes. They could not. Their perception was normal, but their memories were enhanced, creating the illusion of slow motion in retrospect. Children often feel that time passes slowly, while adults commonly feel it speeds up with age. One explanation is proportional theory. A year to a 5-year-old is 20% of their life, a huge proportion. A year to a 50-year-old is only 2%, almost negligible. So, subjectively, a year feels longer to a child. Another explanation involves novelty. Children experience many new things, creating rich, distinctive memories. A day at the zoo is remembered vividly. These rich memories make durations feel longer in retrospect. Adults settle into routines. Days blend together with fewer distinctive memories, making time seem to pass more quickly. A week at a boring job might be remembered as a single undifferentiated blur, feeling shorter than it was. Experiments show that familiar routes seem shorter than unfamiliar ones, even if they take the same time. When you drive a new route, you pay attention to landmarks, turns, and directions, creating detailed memories. When you drive a familiar route, you can do it on autopilot, arriving with little memory of the journey. The familiar route feels shorter because your brain compresses the experience. Time perception is also malleable in extreme situations. Drugs and altered states of consciousness can distort time perception. Psychedelics can make minutes feel like hours or dissolve the sense of time entirely. Cannabis often makes time feel slower. Stimulants can make time feel faster. Meditation practices aim to alter the experience of time, helping practitioners become more aware of the present moment or even transcend the sense of temporal flow. Advanced meditators report states where time seems to stop or lose meaning, where the distinction between past, present, and future dissolves. These phenomena show that time, as we experience it, is constructed by the brain and can be manipulated. This does not mean physical time is illusory, but our experience of it is not a direct perception of reality. It is a model built by our brains, shaped by attention, memory, emotion, and expectation. Understanding this helps explain why time feels so variable and subjective, even though physics describes it as a mathematical coordinate. The relationship between subjective time and physical time is complex and not fully understood. The hard problem of time is explaining why we have a subjective experience of time passing at all. Why does time feel like something? This is analogous to the hard problem of consciousness. We can explain the mechanisms of perception, memory, and information processing, but explaining the qualitative feel, the qualia, of temporal experience remains mysterious. The relationship between time and consciousness is one of the deepest mysteries in science. Why do we experience time at all? Why does consciousness seem to move forward through time, illuminating one moment after another? The easy problem of consciousness, as philosopher David Chalmers calls it, is explaining how the brain processes information, integrates sensory data, and produces behavior. This is a matter of neuroscience and can, in principle, be solved by mapping neural circuits and understanding computational processes. The hard problem is explaining why this information processing is accompanied by subjective experience. Why is there something it is like to be conscious? Similarly, the easy problem of time is explaining how we measure intervals, remember the past, and anticipate the future. The hard problem is explaining why we feel time passing, why there is something it is like to experience temporal flow. Some theories propose that consciousness itself is fundamentally temporal. The act of being conscious might inherently involve the passage of time. One idea is that consciousness is a process, not a state. It requires change and dynamics. A static, frozen brain would not be conscious. Consciousness emerges from the ongoing activity of neural networks, and this activity unfolds in time. The content of consciousness is always changing, as thoughts, perceptions, and emotions arise and fade. This continuous change is intrinsic to consciousness. Another idea is that consciousness integrates information over time, binding disparate neural activities into a unified experience. This integration takes time and creates the sense of duration and flow. Others suggest that consciousness arises from physical processes that are inherently irreversible, tied to the increase in entropy. Without entropy increase, there would be no distinction between past and future, and perhaps no consciousness either. The arrow of time gives consciousness its direction. We remember the past, not the future, because memory formation is an entropy-increasing process. Memories are physical traces, changes in brain structure that record information. Creating a trace increases entropy. Erasing a trace also increases entropy. The asymmetry of memory gives us a psychological arrow of time aligned with the thermodynamic arrow. Consciousness might require this arrow to function. A conscious being that remembered the future as well as the past would experience reality very differently. They might not have free will in the usual sense, since they would know their future choices. Another angle on time comes from the study of biology and circadian rhythms. Almost all living organisms, from bacteria to humans, have internal clocks that regulate biological processes on roughly 24-hour cycles. These circadian rhythms are not learned. They are genetically encoded and persist even in the absence of pollution. External time cues like sunlight. Experiments where people live in caves without clocks or daylight show that humans naturally adopt a rhythm close to 24 hours, usually slightly longer, around 24.2 hours. The molecular mechanisms involve feedback loops of gene expression. Certain genes produce proteins that accumulate over time and eventually inhibit their own production, creating oscillations. These biochemical oscillators are remarkably precise and are synchronized to the external day-night cycle through light-sensitive proteins in the retina. Circadian rhythms affect sleep, metabolism, hormone release, body temperature, blood pressure, and even cognitive performance. Your alertness, mood, and mental abilities vary throughout the day according to your circadian phase. Most people have a dip in alertness in the early afternoon, the post-lunch dip, even if they do not eat lunch. This is driven by circadian rhythms. Jet lag occurs when your internal clock is out of sync with the local time, causing fatigue, confusion, and discomfort until your clock adjusts. It typically takes about 1 day per time zone crossed to fully adjust. Shift workers who must stay awake at night and sleep during the day often struggle because they are fighting their circadian rhythms. This can lead to health problems, including increased risk of cardiovascular disease and metabolic disorders. The existence of circadian rhythms shows that time is biologically embedded. Evolution has equipped organisms with sophisticated timing mechanisms because predicting environmental changes provides a survival advantage. A plant that opens its flowers before dawn can attract early pollinators. An animal that forages at the optimal time avoids predators or extreme temperatures. These internal clocks operate independently of external time, demonstrating that organisms do not passively experience time, but actively generate temporal structure internally. This raises interesting questions about subjective time in different species. Do all organisms experience time the same way? Experiments suggest that smaller animals with faster metabolisms perceive time more slowly. A fly, with its rapid neural processing, perceives events in slow motion compared to a human. This allows a fly to react to a swatter that, to us, seems to move quickly. To the fly, the swatter approaches slowly, giving time to escape. Studies where animals are trained to respond to visual stimuli at different flashing rates support this. Smaller animals can perceive higher flicker rates before the flashes merge into continuous light. This is called the critical flicker fusion frequency. Flies have a much higher CFFF than humans, meaning they can distinguish individual flashes at rates that appear continuous to us. This suggests their temporal resolution is finer. They experience more moments per second. A second to a fly might feel like several seconds to us. Larger animals with slower metabolisms might perceive time more quickly, though this is harder to test. An elephant or whale might experience a year as feeling shorter than it does to us, though this is speculative. Plants present an even more alien perspective on time. Without a nervous system, plants cannot have subjective experiences in the way animals do, but they respond to time. They grow toward light, a process called phototropism. They open and close their leaves on daily cycles, a behavior called nyctinasty. Some species can even measure the length of the night to determine the season, a process called photoperiodism, which triggers flowering at the right time of year. Time-lapse photography reveals that plants are constantly moving, just too slowly for us to notice in real time. Vines circle as they grow, searching for support. Flowers track the sun across the sky. Mimosa plants fold their leaves when touched and gradually reopen over minutes. Do plants experience time? Almost certainly not in any way we would recognize. They lack brains or centralized processing. Their temporal processing is chemical and distributed, operating on timescales of minutes to hours rather than milliseconds. Yet they are temporal beings, structured by and responsive to time's passage. This spectrum of temporal experience, from the fly's high-speed perception to the plant's slow chemical rhythms, suggests that time is not a single universal experience, but something each organism constructs based on its biology. Subjective time is relative not just in the physics sense, but in the biological sense. Each species, each individual, inhabits their own temporal niche. Returning to physics, one of the most profound implications of relativity is the relativity of simultaneity. Events that are simultaneous in one reference frame are not simultaneous in another frame, moving at a different velocity. This is not just about perception, it is a fundamental feature of spacetime. Imagine two events occurring at different locations. In one reference frame, they happen at the same time. In another frame, moving relative to the first, one event happens before the other. A third frame moving in the opposite direction would see the events in reverse order. This sounds impossible because our everyday experience tells us that simultaneity is absolute. If two firecrackers explode at the same instant in my reference frame, surely they explode simultaneously in every reference frame, but they do not. Consider the train thought experiment, a classic illustration. A train moves at high speed. Lightning strikes both ends of the train simultaneously in the ground frame, leaving scorch marks on the train and the ground. An observer on the ground, midway between the strikes, sees the light from both strikes arrive simultaneously and concludes they occurred at the same time. But an observer on the train, also midway, is moving toward the light from the front strike and away from the light from the rear strike. They see the light from the front strike arrive first and conclude it happened earlier. Both observers are correct in their frames. There is no fact of the matter about which strike happened first. Simultaneity is relative. This has bizarre consequences. It means the present moment is relative. There is no universal now. Different observers have different surfaces of simultaneity, different slices through spacetime that they consider the present. Your now includes events that, to a moving observer, are in the past or future. Imagine you are on Earth, and an alien on a planet 10 light-years away is moving toward Earth at half the speed of light. According to relativity, events on the alien's surface of simultaneity, their now, include events on Earth several years in your future. If the alien is moving away from Earth, their now includes events years in your past. This undermines the intuitive notion that the universe exists in a single present moment, marching forward in time. Instead, the universe is a four-dimensional spacetime block, and different observers slice it into past, present, and future in different ways. Philosopher of physics Tim Maudlin argues that this requires us to abandon the idea of a preferred foliation of spacetime into moments of time. There is no single correct way to divide spacetime into instants. Every reference frame provides an equally valid foliation, and none is more real than the others. This supports the block universe view. All of spacetime exists, and different observers pass it differently. However, some argue that this overstates the case. In cosmology, there is a natural choice of reference frame, the co-moving frame defined by the cosmic microwave background. Observers at rest with respect to the CMB agree on simultaneity and define cosmic time. This provides a practical preferred frame, even if it is not fundamentally privileged by the laws of physics. The debate continues. Does the relativity of simultaneity show that the present is an illusion, or does it, to simply show that different observers pass reality differently while all perspectives remain valid? What is undeniable is that simultaneity is not absolute. The universe does not have a global now in the sense we intuitively imagine. This connects to another strange feature. In special relativity, The order of events can be reversed for some pairs of events, but not all. If two events are separated by a time-like interval, meaning one could causally affect the other, all observers agree on their order. Event A happens before event B in all frames. If two events are separated by a space-like interval, meaning they are too far apart for light to travel between them, their order is relative. Some observers see A before B, others see B before A. This preserves causality because space-like separated events cannot influence each other. No signal, information, or causal effect can travel between them. Only time-like separated events have a definite order, and those are the ones that can be causally related. Another consequence of relativity is length contraction. Objects moving at high speeds are shortened in the direction of motion from the perspective of a stationary observer. A spaceship traveling at 90% of the speed of light would appear less than half its rest length to an observer watching it pass. To the crew inside the spaceship, nothing has changed. The ship feels normal length, but distances outside the ship are contracted. The destination star, which is 10 light-years away in the rest frame, is only about 4.4 light-years away in the ship's frame. This symmetry is key. Length contraction is not something that happens to the moving object. It is a change in the relationship between reference frames. Both observers are correct in their measurements. There is no objective length independent of reference frame. Just as with time, space itself is relative. Combining time dilation and length contraction leads to the resolution of paradoxes, like the barn pole paradox. Imagine a pole that is 10 meters long and a barn that is 9 meters long, both measured in their rest frames. The pole does not fit in the barn when both are at rest, but if the pole is moving at high speed, it contracts and can fit inside. You could, in principle, close both barn doors with the pole entirely inside for an instant. From the pole's reference frame, the barn is moving and contracted, so the barn is even shorter and the pole should not fit. Who is correct? The answer involves careful analysis of simultaneity. In the barn's frame, there is a moment when the contracted pole is entirely inside the barn, between the two doors. In the pole's frame, there is never a moment when the pole is entirely inside the contracted barn. Both are correct because they define simultaneity differently. The events of the front of the pole entering the barn, the front of the pole exiting the barn, and the back of the pole entering the barn are not simultaneous in both frames. In the barn frame, the front exits after the back enters, allowing a moment when the pole is entirely inside. In the pole frame, the front exits before the back enters, so there is never a moment when the pole is entirely inside. If you close both doors simultaneously in the barn frame, in the pole frame, the doors do not close simultaneously. The front door opens before the back door closes. Both descriptions are consistent with the events. Relativity consistently resolves these apparent contradictions, but it requires abandoning absolute notions of length, time, and simultaneity. The universe is stranger than our intuitions suggest, and relativity forces us to accept this. The speed limit of light is central to all of this. Nothing with mass can reach or exceed light speed. As an object accelerates toward light speed, its relativistic mass effectively increases, requiring more and more energy to accelerate further. The energy required to reach light speed is infinite, which is impossible. Only massless particles, like photons, can travel at light speed, and they always do, in all reference frames. They can never be at rest. From a photon's perspective, if it had one, the journey from a distant star to your eye takes 0 time. The photon is emitted and absorbed in the same instant because time does not pass for something traveling at light speed. The photon's world line is a null geodesic, a path where the proper time is 0. This is another strange consequence of relativity. Light experiences no time. The universe, from light's point of view, is timeless. All events along the photon's path occur simultaneously for the photon. Of course, photons do not have a perspective in any meaningful sense, but the mathematics describe this limiting case. Faster than light travel, often called FTL, is a staple of science fiction but appears to be impossible in our universe. Special relativity forbids it. Traveling faster than light would allow you to violate causality, sending signals into the past and creating logical contradictions. If you could send a signal FTL, there exist reference frames where the signal arrives before it is sent. You could send a message to your past self. This creates paradoxes. However, general relativity offers loopholes. Space-time itself can expand faster than light, as it does during cosmic inflation in the early universe. An object at rest in expanding space can recede from us faster than light if the space between us expands quickly enough. This does not violate relativity because the object is not moving through space faster than light. Space itself is expanding, the object is just carried along. Another loophole is the Alcubierre drive, a speculative concept proposed by physicist Miguel Alcubierre in 1994. The idea is to create a bubble of contracted space in front of a spacecraft and expanded space behind it. The ship rides inside the bubble, where space-time is flat and normal. The bubble itself moves through space-time, effectively surfing on a wave. The ship does not exceed light speed locally within the bubble, but it can travel arbitrary distances in arbitrary time because space outside the bubble is being manipulated. Unfortunately, the Alcubierre drive requires exotic matter with negative energy density, which probably does not exist in the required amount. The energy requirements are astronomical, possibly requiring the mass equivalent of Jupiter or larger. Even if it were possible, the front of the bubble might accumulate high-energy particles that would be released upon arrival, potentially destroying the destination. It remains an interesting theoretical curiosity, but not a practical propulsion method. Wormholes offer another theoretical FTL possibility. A wormhole is a shortcut through space-time, connecting two distant locations. If traversable, you could enter one mouth of the wormhole and exit the other, instantly appearing light years away. General relativity allows wormhole solutions mathematically. The simplest is the Schwarzschild wormhole, but it is not traversable. It connects two black holes, and nothing can pass through because the throat of the wormhole collapses too quickly. To make a wormhole traversable, you need exotic matter with negative energy density to hold it open. Again, such matter has never been observed and may not exist. Even if traversable wormholes could exist, creating one and moving it to a useful location might be impossible or require more energy than we can harness. Some physicists also worry that traversable wormholes could enable time travel by creating a time difference between the two mouths. Moving one mouth at high speed would cause it to age less than the other due to time dilation. Traveling through the wormhole would then transport you to a different time. This leads to causality paradoxes. Stephen Hawking's chronology protection conjecture suggests that the universe prevents time machines, possibly by causing wormholes to collapse or quantum fluctuations to destroy them before they can be used for time travel. Again, these remain speculative. No one has observed a wormhole or exotic matter. They exist in theory, but not, as far as we know, in reality. Time continues to be the deepest mystery in physics, more so than space, matter, or energy. We have learned that time is not what it seems. It is not a universal, flowing river. It is not absolute or independent of space. Time bends, stretches, and breaks. It is relative, observer-dependent, and intertwined with space into spacetime. The present moment is not universal. Simultaneity is relative. The future and past might be as real as the present in the block universe. Or time might not be fundamental at all, but an emergent property of entropy, quantum mechanics, or consciousness. We measure time with extraordinary precision using atomic clocks, yet we cannot say what time truly is. We know the equations that describe how time behaves, but we do not understand why time feels the way it does. The flow of time, the arrow of time, the experience of now, these remain mysterious. The quest to understand time drives some of the most exciting research in physics today. Scientists build ever more precise atomic clocks to test relativity in new regimes. Optical lattice clocks now reach precisions where they can detect time dilation from height differences of a single centimeter. This opens possibilities for precision tests of general relativity and searches for new physics. Gravitational wave detectors like LIGO observe ripples in spacetime from colliding black holes and neutron stars, testing general relativity in extreme conditions where gravity is strong and dynamical. So far, every observation confirms Einstein's predictions. Quantum gravity theories attempt to unify relativity and quantum mechanics, which might reveal whether time is continuous or discrete, fundamental or emergent. Loop quantum gravity, for instance, predicts that space-time has a discrete structure at the Planck scale, with minimum units of area and volume. Time would also be quantized, advancing in discrete steps. String theory, another approach, suggests that fundamental particles are tiny vibrating strings, and space-time emerges from the interactions of these strings in higher dimensions. In string theory, time might be an effective description that emerges at large scales but breaks down at the fundamental level. Causal set theory proposes that space-time is fundamentally a discrete set of events with causal relations, like a graph. Continuous space-time is an approximation. These theories are speculative and lack experimental confirmation, but they represent serious attempts to understand time at the deepest level. Philosophers and neuroscientists study the psychology of time perception, trying to understand how the brain constructs our subjective experience of time. Brain imaging studies reveal that time perception involves distributed networks, including the prefrontal cortex, basal ganglia, and cerebellum. Different brain regions track different timescales, from milliseconds to hours. Neurotransmitters like dopamine influence time perception. Parkinson's disease, which involves dopamine loss, is associated with impaired timing. Stimulating dopamine pathways can alter time perception. Understanding the neural basis of time perception might explain the hard problem of why we feel time passing, though this remains an open question. Cosmologists map the universe's large-scale structure and measure its expansion, piecing together its history from the Big Bang to the present and projecting into the future. Observations of distant supernovae, the cosmic microwave background, and large-scale galaxy distributions constrain models of cosmic evolution. The discovery that the universe's expansion is accelerating led to the inference of dark energy, a mysterious component driving the acceleration. Understanding dark energy is crucial for predicting the universe's fate. Will it expand forever, leading to heat death? Will dark energy change, leading to a big rip or big crunch? These questions about the future of time in the cosmos remain unanswered. All these efforts converge on the realization that time is far stranger than common sense suggests. It is not a simple, universal ticking clock. It is a flexible, relative, possibly emergent feature of reality, woven into the fabric of space-time, shaped by gravity and motion, and perhaps ultimately reducible to something even more fundamental that we have yet to discover. Every major advance in physics has changed our understanding of time. Newton introduced absolute time, a universal clock ticking at the same rate everywhere. Einstein shattered this, showing time is relative. Quantum mechanics suggested time might be linked to entropy and the collapse of wave functions. Quantum gravity might show time is discrete or emergent. Each step reveals deeper strangeness. Our journey through the nature of time has taken us from Einstein's patent office to the event horizon of black holes, from the Big Bang to the heat death of the universe, from the ticking of atomic clocks to the flow of subjective experience. We have seen that time is relative, that simultaneity is observer-dependent, that time dilation is real, and that the universe has no universal clock. We have explored the possibility that time is an illusion, an emergent property of entropy and consciousness, and considered scenarios where time begins, ends, or loops back on itself. We have confronted paradoxes, puzzles, and unsolved mysteries that challenge the brightest minds in science. What does all this mean for you, right now, reading these words? It means that your experience of time is unique. The seconds you experience pass at a different rate than someone in orbit, or someone traveling at high speed, or someone near a black hole. It means that the present moment you feel is not universally shared. It is your personal slice through space-time, defined by your motion and location. It means that the past and future might be as real as the present, existing eternally in the block universe of space-time. Or it might mean that time is a construction, an emergent feature arising from entropy, consciousness, and the way your brain organizes information. It means that time travel to the future is possible, though impractical with current technology, and that travel to the past might be forbidden by the laws of physics, or might require exotic matter and enormous energies we cannot harness. It means that the universe began 13.8 billion years ago, in cosmic time, though from other perspectives, different amounts of time have passed. It means that the universe might end in heat death, or a big rip, or a big crunch, or it might cycle forever. It means that we live in a brief, special epoch when the universe still has structure, when stars shine and galaxies cluster, when entropy is increasing but not yet maximized, when time's arrow points clearly from past to future. In the far future, billions or trillions of years hence, the universe will be a colder, emptier place, and time might lose its meaning as entropy approaches its maximum. Most fundamentally, it means that time is not what it seems. It is not a river carrying us along. It is not an external clock ticking away independent of the universe. It is part of the fabric of reality, inseparable from space, shaped by mass and energy, and experienced differently by every observer. It is possibly not even fundamental, but an emergent property of something deeper, something we have not yet fully grasped. The nature of time is one of the great frontiers of science, a mystery that touches every aspect of existence. Understanding time means understanding the universe and our place within it. The quest to understand time continues, driven by curiosity, ingenuity, and the profound human need to know what it all means. Every experiment, every observation, every theory brings us closer to the answer, but each answer reveals new questions, deeper mysteries. Time is the dimension of change, the parameter along which events unfold, the measure of causality. Without time, nothing would happen. The universe would be frozen, static, but time is also the dimension of loss. Every moment that becomes the past is gone forever, at least from the perspective of subjective experience. We cannot return to yesterday. We cannot relive lost moments. This gives time an emotional weight that space does not have. We can move through space freely, but we are prisoners of time, swept forward whether we want to be or not. This asymmetry is poignant. It underlies our sense of mortality, our awareness that life is finite and precious. Yet physics suggests a different perspective. In the block universe, nothing is lost. Every moment exists eternally in space-time. Your childhood, your first love, your greatest triumph and deepest sorrow all exist forever as events in space-time. They are not gone. They are just located at different time coordinates than your present reading of this text. From this view, death is not an ending, but a boundary. Your world line terminates at a certain point, but the life you lived exists eternally in the space-time manifold. This is a kind of immortality, not in the sense of endless duration, but in the sense of timeless existence. Every moment of every life persists, unchanging, in the four-dimensional structure of reality. Whether this brings comfort or not depends on your philosophy. Some find solace in the idea that nothing is truly lost, that the past is preserved. Others find it unsettling, preferring the sense that the past is gone and the future is open. The block universe implies a form of determinism. If all moments exist and the future is as real as the past, then the future is already determined. Your choices, from this view, are part of the structure of space-time. You will make the choices you make because that is what your world line does at those coordinates. Free will, in the libertarian sense of having multiple possible futures, any of which you could choose, seems incompatible with the block universe. But compatibilist views of free will, where freedom means acting according to your desires without external compulsion, remain viable. You are still the cause of your actions, even if those actions are deterministically fixed in spacetime. These philosophical questions do not have clear answers, and physics alone cannot resolve them. Physics tells us how time behaves, what its properties are, how it relates to space and matter, but physics cannot tell us what time means for human existence, how we should relate to our mortality, or whether free will exists. These are questions for philosophy, informed by science but not determined by it. What science can do is strip away false certainties and reveal the strangeness of reality. Time is stranger than we imagined. The universe is stranger, and our existence within it is more mysterious and wonderful than common sense suggests. You are traveling through time at a rate that is measurably slower than most of the universe. This is not science fiction. This is your reality. Every moment you experience is shaped by your speed, your position in a gravitational field, and the structure of space-time itself. Time is relative. Time is flexible. Time is strange. And you are part of its mystery. Right now, as you read this, time is bending around you, flowing at its own rate, defining your experience of existence. This is the universe we inhabit. This is the cosmos revealed by physics. This is the nature of time, and it is far stranger than anyone imagined. The journey to understand time is not complete. It may never be, but every step forward reveals new wonders, new depths, new questions. We are creatures of time, living brief lives in a vast cosmos, seeking to understand the framework that gives our existence meaning. That quest continues, and as long as time flows, or seems to flow, we will continue asking, what is time? Why does it exist? And what does it mean to live within its flow?